Okay, so board cleaned. Let's do theorem 29. Which involves the identity function. Okay, so you're given a function f that maps a to a, right? So, and the theorem is the following. I of a, remember the identity function maps any element of big A to itself, right? That's for all A belonging to the set A. Right? That's the definition of the identity function. It doesn't do anything, it doesn't change anything. It operates, but the effect's the same, right? So it just maps something to itself, right? But f is just an arbitrary function, mapping between A and A. So what happens if you make a composite function where one of the two functions is I? Interesting question. So here's so if you do AIF, so you apply F first, then you apply the identity function, you will get just F. Right? That seems sort of intuitively fairly obvious, right? You apply F and then you effectively do nothing. So the result of that will be just F, right? Seems plausible. So we'll prove it. And if you reverse these two, you get the same. You also get F. Now, why does that seem plausible? Well, if at first you do nothing, so obviously nothing changes, and then you do F, the result will be the same as if you only did F. Right? So that's the theorem. Now that's what we have to prove. So let's try this one. So IA of F applied to little a. So let's say make it a composite function. So so this is the same thing as okay. You can rewrite this as okay. That's the definition. That's the definition of the identity function. Right? I times something just gives you the something. So I operating on this will just give you f of a. Right? So IF is f. Here it is, IF is f. Now let's go the other way. So f, can you see that? F, binding operator, that's the term I was looking for before. And you apply that to little element, to little a, the element. So you can rewrite this as f of IA of a. Okay. Now it's the identity function, so this is just, inside here is just a, little a, so this becomes, right? So there's your proof. So IF is F, and FI is F, okay? So this I is your identity function. And we will use that a bit later. All right. Now introduce the concept of of an inverse function. Now you're probably getting a bit suspicious where I'm going with all this. This is a course on group theory, right? And here I am, I've just talked about an identity function which sort of has no effect, and that's sort of like the identity, the unit element in group theory, and we're talking about all this stuff within the context of group theory. So probably where I'm heading is, you're talking about all this stuff, is the punchline at the end of the lecture will be where we create some kind of group, right? So all these theorems and so forth, it's easy to lose track of where you're going. There's an expression in English that if you, how does it go? Not seeing the wood for the trees. Now wood, not in the sense of the wood that you burn, but wood as in forest. If you stand too close to the forest, too close to the wood, all you see is trees. You don't see the whole thing. You don't see the big picture, in other words. I mean, if you stand right up close to a tree, you don't see the forest at all. Right? So a lot of all these theorems and so forth, you may be asking, well, where's all this headed? What's the motivation behind all these theorems? And the answer is that we're showing properties that will, at the end of the day, so to speak, we'll be able to prove that there's a kind of group that's you can define that involves composite functions. Right? That's the main idea at the end of the lecture. All right. Okay. So next concept is inverse function. So if you're talking about groups, every element in a group has an inverse, right? Which is sort of cancels out the element to leave you with the unit element. So if there's a function f, question. If you have a function f that takes you from A to B, so if you have f takes you from A to B, is there a function that takes you the other way? Can you, in a sense, go back? So question mark, is there a function g that takes you from B to A so that you end up with what you started with? Right? Is that possible? And if it is possible, are there certain restrictions, like on f? Like f, does f have to have certain properties that enable g to exist? You can start speculating on questions like that, and that's the nature of math. If you're a research mathematician, you'd be asking questions like this. So, in pictorial terms, in pictures, so here's your function f, which maps little a into little b, little a from set A, your domain, into set big B, your codomain. So it maps little a into little b, right? Now, is there a function which cancels that out, in a sense, starts with b, maps little b back into little a? So can that be done? Is there a function g that allows that? So f of little a would map to b, right, to this point, and then g, if it exists, would take you back. So you would map then little b back to little a. So if you did first f and then g, you would end up where you started with, right? So if that's possible, if a g does exist, then gf, and remember the order. Remember the right-hand one is the one that operates first, right? So first f, then g. So f takes you to here, and g would take you back. So if that g can exist, then this is just the identity, right? It's the identity operator for set A, right? Because you do f first, and then come back. Right? So you'd end up with little a if this g exists. Okay, so the big question now is, it'd be nice if it did exist, because then you could have inverse, like in a sense like reverse, does the opposite, cancels out the effect of F. It sort of undoes the mapping. So your F maps you to B, and then your G unmaps you in a sense, or like a reverse mapping, so this G would be an inverse function if it can do that. All right. So what properties does F need to have for that G to exist? Well, let's speculate. Let's say, well, we can ask, is F, say, injective, or surjective, or bijective, right? So 3 possibilities. Well, let's start thinking a bit. If it's injective. Okay, so imagine. So here's A, and here's B. Here's A and B. Now let's say F is injective. Now injective means map to, each element in your codomain is mapped to at most once. Right? Remember the definition of injective? So you could have okay, so let's say there are only 2 elements in A, and let's say 3 in B. They're different sets. Okay, we're not mapping in this case A to A. We're mapping A to B. A general case. Let's say, and this mapping here, F, is injective, right? So each element of your codomain is mapped to at most once. Okay? So this is mapped once, this is mapped once, and this is not mapped at all. Okay? So if you wanted a G to take you back, what on earth do you do with this point here, this element here? Right? There's no connection with F. So how can you use F in some sense to get you back? It's not even mapped to. So it looks as though if F is injective, that's not going to work. That makes you deeply suspicious. Right? So probably an injective F is not going to work. All right. So